So the last speaker of this first of the two afternoon session is Kenwin Maung from Rutgers University, and he is talking about estimating high-dimensional Markov-switching VARs. Thank you, Kenwin.
Thank you for having me over. Actually, the question that I'm asking here today is very simple. Basically, I'm asking how do we estimate Markov-switching VARs, vector autoregressions, when the dimension of our system is really large? So just to lay some groundwork, although Frederick gave a really good introduction to Markov-switching AR models, I'm going to consider the vector case. And this tends to be a more commonly used model when we talk about macroeconometrics. And we have a vector YT of endogenous variables over here. And you could also allow it to have some dynamic dependence. That's where the AR structure come from. You can have it, have some exogenous variables in your system too. So the difference between a VAR and that of a Markov switching model over here is that everything, all the parameters of our model are allowed to depend on some sort of latent state, which is given by ST, and ST would be assumed to be following some sort of first order Markov chain. I'm assuming a very simple model. Where is the high dimensionality in this model? Well, we're basically going to let the number of variables in our system to potentially increase over time. The number of lags can also increase over time. On the first point, what it means in the finite sample, which basically just means that you could have a lot of variables in your YT. So YT is going to be like a larger dimension. And in this case over here, when we look at the model, then it's just basically all of the, the number of lags and number of variables in a vector are going to be indexed by capital T, and capital T is going to be a sample size. So it's a relatively simple setup. But the estimation of this model might not be that straightforward because the number of parameters here that define the system would be, as it goes to infinity, would definitely exceed the sample size. So how do we deal with such a situation? That's the question that I'm asking here. So this is important because if we look at macroeconometrics, or even in finance, there are a lot of Markov switching models. And I think people like it over there because you have this idea of discrete states, and you want to look at how macroeconomic relationships can change depending on whether you're in a recession or whether you're in an expansion. And in finance, whether or not you're in a bull market or you're in a bear market. So if we look at all of these applications using Markov switching VARs, you see that you can use in monetary policy, forecast combinations, short horizon, excess return predictability. And on this point over here, this would be the application that I would consider in my model today. And just a little bit of a spoiler, what they find in this paper over here is that, you can have excess return predictability when the economy is in a recession, much more so than you would have in an expansion period. So I would like to try to replicate this result. So the issue is a lot of these models are basically just lower dimensional models, but many macro questions are about high dimensional endogenous systems. But there is a necessary limitation to that because if we were to try to model such large systems, we would have parameter proliferation. So it's not going to be computationally feasible to estimate such models. Even in the simplest linear vector autoregression case, if you want to estimate the model by equation least squares, if you have too many parameters or too many variables in a system, then the least squares estimate is not going to be unique. And this is even worse in our case because we are estimating everything using maximum likelihood and it has to be in a system estimation framework. And also forecasting or policy analysis where you have a small number of variables, you would necessarily, or you would likely incur some sort of omitted variable bias. And in this case, I think the leading example would be the price puzzle in vector autoregressions. In that situation, if you run a simple linear VAR with just 3 variables, say output, inflation, and interest rate, what you might realize is that if you have a positive shock to interest rate, people have often observed that the inflation increases, which is very counterintuitive. And what people have also found out is that if you were to include more variables to the system, for example, if you include inflation expectations, that puzzle seems to dissolve. So that is a very obvious example of an omitted variable bias that affects a policy analysis, policy prediction of a monetary policy shock. So the traditional responses in this situation would be, you could use aggregated data. Say if you want to study the stock market, you instead of including individual stock returns, you would just use, say, S&P 500. That would help you save on the degrees of freedom. You could also basically either use an ad hoc method or using economic theory to select the endogenous variables. But then again, that might potentially incur that kind of omitted variable situation. So there's also factor augmented approaches. Like we just saw, you would just extract the common factors from a cross-section of variables and to include the factors in the VAR itself. You can also consider Bayesian estimation. Not so traditional methods, which I think it's not so traditional back then, but it's probably more traditional right now, is to use some of the penalized estimation method, such as lasso, adaptive lasso, and this paper, Khaled and Koch, they apply that to the simple linear vector autoregression case. And also there's some non-concave penalties, such as the smoothly clipped absolute deviation penalty. So I would continue this so-called, I guess, not so traditional approach and adopt a sparse framework. And what we mean over here is that we're just going to assume that even though we have a potentially high dimensional VAR, at the end of the day, the variables that truly matter in a VAR are not that many. So there are a lot of zeros in our coefficient matrices. A lot of these variables have zero coefficients, and only a small subset of these variables would have a non-zero coefficient. So we're gonna use some penalization to extract. The issue here is that we don't know which variables are going to have non-zero coefficient to begin with. So we're going to use some sort of penalized estimation method to identify that sparse support of those coefficient matrices. And we're going to study the simple lasso case where you have the L1 penalty, and you could also have the smoothly clipped absolute deviation penalty, which is often defined by its first derivative given over here. The reason why we have these two penalties is that it is known that the lasso penalty it's notorious in not being able to recover it's not consistent. It requires very strong high-level assumptions to consistently identify which variables are important or which variables are relevant, while the scat penalty requires fewer assumptions. Now, furthermore, the reason why this is very interesting in a Markov-switching framework is that you're able to identify which variables are important in which state of the economy. So you're able to see what type of variables are important to your system during, say, recession states or during expansion states. So the extension to Markov-switching VAR, as I mentioned, people have done this for a linear vector autoregression, is that computationally and theoretically speaking is a bit more challenging because we have a system estimation with maximum likelihood compared to just using an equation by equation approach in a linear VAR. And also the choice of using the scat estimator or the scat penalty here is that it tends to yield many local optimal points. And unfortunately, the asymptotic results that we have tend to only be developed for a theoretic local optimum. So to counteract that, we're going to use this so-called local linear algorithm to, instead of trying to identify that local optimal point for which the theoretical properties will satisfy for that, we're going to use this local linear algorithm to try to bind the probability that we have found a theoretic local optimum. So that unpenalized likelihood, the log likelihood of Markov-switching VR is entirely standard. This is just the mixture densities, mixture of densities. And the only difference is that we're just going to add the penalty terms over here. So in the first lasso, if we were to use the lasso case, we would penalize the coefficients for our coefficient matrices, both the AR part and also the exogenous part. We're also going to penalize the off-diagonal terms of our variance covariance matrix. For the scat problem, we're just also going to do the same thing. However, if you notice in the scat penalty term, we do need to have some sort of initial values to run the scat penalty problem. And the reason why I suggest both the lasso and the scat problem is because I will be using the lasso estimates to initialize the scat problem. And this leads to what we call the local linear algorithm. The idea here is that if we can initialize the scat problem with some sort of what they call a localizable estimate or a good initial estimate, then with probability approaching 1 or high probability that the computed solution to this problem over here would give you that theoretical optimal point that we're interested in identifying. Okay. So in terms of estimation, we're just going to use the EM algorithm because we have the latent states. And I propose in the paper for the typical setup of the Gaussian distribution. the expectation step is going to be unchanged, but the maximization step is slightly different. It's just a slight change, in the sense that we're just going to fix the regime S in like what you usually do. And instead of using maximum likelihood for a linear regression, you just use a penalized likelihood with the lasso and the scat penalties. So this can easily be done in statistical packages because of all these really fast packages or codes that have already been programmed. So there are two sets of conditions that we require over here. Because the structure of this paper is relatively general in the sense that I don't assume that we have, at least in the theory section, we don't assume that we have a normal distribution. So all the theory would hold for very general distributions too. And because we have that high dimensional aspect, we would also assume the typical regularity conditions for high dimensional models, for example, like a restricted eigenvalue condition. So under all of those conditions, we can show that the lasso estimator will give you a consistent estimate. However, we don't present any results related to the consistent selection of the lasso estimator because, like as I mentioned, as a preface earlier, those require really strong assumptions which are really unlikely to hold in a typical economic setting. So we will not do that. We're just going to show that it's consistent in the sense that the vector norm would go to 0. And given that, if we were to initialize the scat estimator with the lasso estimates, we can show that the scat estimator would be estimation consistent, and also with probability approaching 1, it's going to identify the right zeros in our problem, in our VAR. So it's able to consistently select the relevant variables. And conditional on selecting the relevant variables, then we can also have some sort of asymptotic normality for our scat estimator. So over here, I have a very simple simulation setup. I would have actually, initially when I came up with the simulation setup, I thought this was a very simple one, but this is the most extreme case in the sense that the VAR is actually not a VAR. This is the coefficient matrices of the VAR1 is just going to be a diagonal matrix. So effectively, all of our variables follow an AR1 process. So this is probably the sparsest case that you can consider for our VAR, for the so-called high dimensional VAR. And for the second state, the coefficient matrix is just a negative of that. So we consider the case where we have 10 and 16 variables. The reason why I chose 16 variables is so that it's going to be consistent with our empirical application. They're relatively low. I mean, if you think about, ultra high dimensional problems, they're relatively low. But even in such situations, the usual cases of the usual approaches of estimating such models would likely not be able to handle that. So that's why I considered these numbers. And as you can see over here, if we look at the mean square error, we do seem to have, as the sample size increases, we do seem to have, some sort of estimation consistency going on. In terms of selection consistency, if we focus our attention on the number of selected parameters, as the number of selected parameters decrease, and it seems that the percentage of iterations that include the true model seems to also be increasing. So that gives us some evidence that we have some sort of selection consistency going on. So I would like to talk a little bit more about the application that I have today, and this has something to do with the countercyclical return predictability. There's a lot of literature that shows that our stock returns tend to have a greater degree of predictability when we are in a recession and not so much in an expansion period. So this is the main JFE paper that I'd like to replicate. And they estimated MSVAR with two states. They have expansion and recession, and they have 5 endogenous variables. They have excess returns and 4 commonly used predictors: the dividend yield, the short rate, the term spread, and the default spread. So the main equation of interest in this model would be the first row, because the excess returns is in the first row, because on the left-hand side, you have excess returns, and on the right-hand side, you have lagged excess returns, you have lagged predictors too. So that's the main equation that they are interested in. So my gripe with this model is that they don't really give a good reasoning they don't really tell us why they chose those variables to begin with. And also the finding that, the return predictability depends on recession and expansion. I mean, that could be due to other variables that are not included in that model. So this could be more of a omitted variable bias critique. So I include 14 predictors that people commonly use and study by going on Welch, and these are the main 14 predictors. The 4 predictors used in the original paper are a subset of these 14 predictors. And we estimate this MSVR using the scat penalty initialized by the lesson. So the first set of results I'll show you is that of the smooth probabilities. So the crosses over here are going to be the smooth probabilities implied by my model. And on this blue, the teal line over here is going to be the MBER recession indicator. So the match between the recessions, the states implied by my model and that of the MBR recession indicator is about 70%. And the original model, the GFE paper, that is about 77%. And in terms of the state transition probabilities, it's also very closely related to the original estimates. But what is different from my paper and what they found earlier is that if we look at so as I mentioned earlier, the first line of that VAR is of particular interest. We want to see how good is the R squared, for how good is the fit for that particular equation. And it turns out that the R squared for the recession is higher than the R squared for expansion. So the original paper argued that this is some evidence that we have greater predictability during recession. And by the way, predictability over here is in-sample predictability. And the R squared expansion is slightly lower than the recession. But what they found in the original paper is that the R squared for the expansion is much lower. It's like 0.05 or something like that. But for me, I do find a slightly higher value compared to them. And I guess that the reason why that's the case is because if we look at the variables that were selected during expansion, the P stock variance and the T-bill rate. Only the T-bill rate was used, overlaps with the original set of variables that the original authors used. The dividend price ratio and stock variance were not included in the original set of variables, original set of predictors. So maybe the relatively higher R squared that I got over here could be due to the fact that the original variables that they chose were not that relevant to begin with. And we also see that in terms of variable selection, we also see that the more variables seem to play a greater role during recession, which kind of does cohere with the idea that we have a greater deal of return predictability during recession as compared to an expansion. So I also do some out of sample forecasting exercise, but in the interest of time, I'd like to conclude that what I've done over here today is basically give you a very simple way to estimate high dimensional VARs using a scat penalty estimator that has been initialized by the lasso, and I provide some asymptotic guarantees on both the estimation and the selection consistency of such an approach. I develop an EM algorithm, a modified EM algorithm to deal with the case where we have Gaussian distributions, and we use this to study a system of return predictability. And we do see a very similar phenomena of countercyclical return predictability. And I would like to stress that this is very interesting, again, in a Markov-switching approach, because you can identify which variables are important in different states of the economy. And I believe that this type of approach can be applicable to more situations than just return predictability. Right. Thank you very much for your attention, and questions and comments greatly appreciated. Alessandra, I think you're muted.